Okay, let's have a crack at problem number 4 from set sac109. We've got a particle at the origin of a coordinate system. Go ahead and draw the coordinate system in there. Call that the plus x direction, the plus y direction, and particle number 1 is at the origin. And it's moving in the plus x direction with a velocity v1, which is constant. Then we got a particle number 2 back here at some negative value of x, but also on the x-axis initially. And it's got an initial velocity v02 at some angle theta. Where the angle theta, they didn't give us a value, but we're supposed to consider it known, but it's v02 that we're looking for. The idea is we're supposed to find the value of VO2 that'll make it so that by the time this particle, number 2, due to a constant acceleration in the minus y direction that it has, gets back to the x-axis, particle number 1 is at the very location at which particle 2 hits the x-axis. So we've got a collision between the two particles. Now the time that it takes 2 to get back to the x-axis is determined by the y motion of particle number 2. So I'm going to study the y motion of particle number 2. To get an expression for a special time, I'll call it TC, the time at which particle number 2 crosses the x-axis, which is also the collision time. So you can think of that subscript as meaning crosses or collision. And particle number 2, y position, is given by its initial y position plus the y component of its initial velocity times t plus 1/2 the y component of its acceleration times t squared. Now it only has a y component to its acceleration. In fact, let's do a quick little vector component diagram for that one. We got A2 is down in the minus y direction. This would be AX and AY in general. So A2y is equal to minus A2. A2x is just equal to 0. So we do have an expression for A2y that we can stick in there. That's A2y, and namely minus A2. We're going to need one for V02y as well. We're given that the initial velocity of particle number 2 is up at some angle there, so let's work on that a little bit. We'll do a vector component diagram for V2. And this would be V2, well, just call it Vx and Vy. I think I want to label those in red. I'm just labeling the axes there. And V2 itself is V2x vector. Notice the arrowheads, make sure you include those, plus V2y vector. And this being a right triangle, V2x over V2 is the cosine of the angle theta at which V2 is directed. And let's write that. V2x over V2 is equal to cosine of theta. So V2x is V2 cosine of theta. I knew I had to break it up into components, but it's the other one that I need, so let's keep going with that. V2y is the opposite to that angle, so V2y over V2 is opposite over hypotenuse, which is the sine of theta, or V2y multiplied both sides by V2 is V2 sine of theta. I'm going to need that right away. I think I'll probably need that later. Yeah, when we're talking about the x motion of particle number 2. So we did our vector component diagrams, which you're supposed to do whenever you're breaking up vectors. Alright, now here's the thing. I'm looking for the special time Tc that makes y2 be 0. And the initial position of particle number 2 was given as 0. So we wind up with an equation that just says 0 is equal to, do the substitutions here, make it pure substitution, v0 to y, and these were all zeros, initial velocities. This was the initial velocity. 0, 0, 0, 0, 0, 0, and 0. Initial velocity in the y direction is VO2 cosine of theta. That's what we just found, times Tc. Put parentheses around that so you don't think I'm taking the cosine of theta Tc, plus 1/2 AY with a minus sign. That was our A2y times Tc squared. Or simplify that a little bit. I'm going to factor a Tc out times V02 cosine of theta plus, except I got a minus sign there, so I'll just write it as a minus 1/2 AY times, and factor just 1 Tc out, so I got Tc left. Check that real quick. Multiply through, I got V0t cosine of theta times Tc, that's this term, plus negative 1/2 AY Tc squared, if I multiply this through, and that's what I got up there, so we're okay. Now, this is 0 if Tc is 0, which just means that one of the times when y2 is 0 is times 0, but we knew that. That's where the particle started. And it's also 0 if this other multiplicand is 0. So let's set that second multiplicand equal to 0 and find the later Tc, the one that's relevant. So minus 1/2 AYTC is equal to 0. That's solves the equation for the case where the second multiplicand is 0. I'm solving for Tc, so I'll add that to both sides and switch sides, this term right here, and wind up with this little equation, which I can solve for Tc pretty easily. I just multiply by 2 over AY, so I get Tc is equal to 2 VO2 cosine of theta divided by AY. Alright. That's the time at which particle 2 crosses the x-axis. Of course, I couldn't evaluate it even by its symbols because we don't know what VO2 is. That's what we're looking for. But let's see where particle number 2, where along the x-axis particle number 2 is. So let's look at the x motion of particle number 2. Go ahead and write that out. X motion of particle number 2 now. So its x position is given by its initial x position plus its initial x velocity, x component of its initial velocity, plus 1/2 its acceleration t squared. And I want to find that at that special time Tc, the collision time, where we're given that Ax is equal to 0, so I can just cross that one out. And I think that's all that is 0 in this case. go ahead and substitute for the V02x what we found from our vector component diagram is V02 times the cosine of theta, and then multiplying all that times TC. So I got an expression for the position of particle number 2 along the x-axis. We know it's on the x-axis because we forced the y to be 0 at time TC. Alright, we need particle number 1 to be at the same position at the same time, so let's figure out where particle number 1 is. At time TC. Particle number 1 is going to be its initial position plus, and it was just moving along at a constant velocity. And again, I want to find it at time TC, that special time. So there was no acceleration for that one, so it's just distance times time. Oh, and it started at the origin. So this term is 0. Now we've got x1 is just that constant velocity v1 times tc. Alright, now at the collision time, these two have to be equal, so we'll go ahead and force them to be equal. Say x1 is equal to x2, and what do we have? v1 tc is equal to x02 plus v02 cosine of theta times tc. And we're supposed to solve for VO2. I better go ahead and substitute our expression for TC into that one. That's this guy. That gives us V1 times TC. Got to take a quick look at it. 2VO2 cosine theta over AY. That's equal to x02, that was some negative value, as we're to the left of the origin, plus VO2 cosine of theta times TC, which I got a copy of right here, so I'll just copy it, 2VO2 cosine of theta all over AY. Did I get that memorized right? I think we got a mistake up here. This was for the y motion. VO2y is VO2 sine of theta. Let's fix that mistake. Everywhere. So sine, 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 and one more place, sine. So when we substitute that in here, it gets substituted in with the sine. That would have been too easy. Alrighty, let's have a look at that then. Got to solve that for VO2. I got a VO2 there. Oh, we're going to have a VO2 squared. Looks like it's going to be a quadratic formula. I think I'd like to go ahead and get rid of the AY. So I'm going to multiply both sides by AY. Just checking to make sure I don't have another algebraic error there, but I think we're looking okay. So I'll multiply both sides by AY, and so this will be just rearranging things slightly up here in the numerator of this guy. Sine theta equals AY times XO2 plus, and then that one gets canceled out. And I'm going to write this as VO2 squared, and then I got the 2 sine of theta cosine of theta. Alright. I got to make this look like a quadratic formula for VO2. I think I'm also going to replace this. I don't know if you recognize that, but that's the same thing as the sine of 2 theta. It'd be okay to leave it the way it is, but I like to take advantage of that trigonometric identity. So I get this piece, sine of 2 theta. I'm going to write down the right-hand side there. Sine of 2 theta times VO squared. And that's actually VO2 squared. And then I'm going to subtract this from both sides. So remember, I'm writing down the right-hand side. So that'll be 2V1 sine theta times VO2. And then also on that side, I got plus AY XO2. And then on the left side, I moved this over, so I just got 0. And this is my quadratic equation. So I'm ready to use the quadratic formula to write down what VO2 is. It's going to be minus B. This would be my B term. 2V1 sine of theta plus or minus square root of B squared minus 4AC. Minus 4. The A is this term. That's the sine of 2 theta. Does that look like a 4? Let's make it look a little bit more like a 4. 4A, and then C is this piece, AYXO2. Alrighty. All divided by 2A. That's 2 times the sine of 2 theta. Let's simplify that just a little bit. VO2 is equal to, minus the minus is a plus, so I can write that as 2V1 sine of theta. And then plus or minus, okay, I want to check this thing out. This sine of 2 theta, it's going to be an angle between 0 and 180 degrees. That's positive on the bottom. This first term is positive. Second term, okay, inside, I got this piece all by itself. If I took the square root of that, it would just be this piece. So it's already as big as that. Let's see if I'm adding or subtracting something. 4, that's positive, positive. This one's negative. So I got a negative, so I am adding something, so the square root piece is bigger than that. So if I use the minus sign, that'll make VO2 negative. But VO2 is supposed to be the magnitude of a vector, and by definition that's positive. So I'm forced from these considerations to choose the positive one. So I need to choose the positive one to make VO2 positive by inspection. And make sure you write down something about that, because I just did a lot with words, spoken words, that is part of the solution. So please write something about that. But let's go ahead and square that. That'll be a 4 times V1 sine of theta, all squared, and then minus 4 times the sine of 2 theta. times AY XO2, initial position of particle number 2 along the x-axis, all divided by 2 times the sine of 2 theta. I think what I'm going to do without writing down an additional step is to factor out the 4. Maybe I better make it another step. Factor out that 4 from both these terms, and then I get 4 times something, and I'm taking the square root of it, so I can take that outside and write it as a 2 times the something. So I can write VO2 is 2V1 sine of theta 1 plus 2 times the square root of all this stuff. And that's all divided still by 2 times the sine of 2 theta. Here's the point. This 2 has to get divided into every term upstairs, but there's a 2 in every term upstairs, so it just cancels out. And we wind up with VO2 is V1 sine of theta 1 plus V1 sine of theta. There was only one theta, so I don't need a 1 on the theta. That's all squared. Minus 4. I think I'm going to switch the order here. Sine of 2 theta. Put in parentheses around that to make it clear that that the 2 times theta is the argument of it. So I'll do that one more time. I'm going to do it up here too. And then all divided by the sine of 2 theta. And that's our answer. That should be the initial velocity of particle number 2 that'll make it so that particle number 2 collides with particle number 1, gets back to the x-axis just as particle 1 arrives at the point where it hits the x-axis, where 2 hits the x-axis. Let's check our units. I'm looking for velocity. This is units of velocity times a pure number as units of velocity. Here we'll have velocity squared. This one, it's meters per second squared times meters. That's meters squared per second squared. So that's also velocity squared. So I can add those two together to get units of velocity squared. Take the square root, and I got units of velocity, which I can add to units of velocity. To get units of velocity up top, divided by a pure number downstairs, means the answer has units of velocity. Quick check to make sure I can really take that square root. Everything in here, I guess we checked that once before, is positive except for this one, which is negative because particle number 2 starts out to the left of the origin. We were told that it's got a negative value. XO2 is known to be less than 0, so we know it's negative. So again, I'm taking this will be positive then. A negative here cancels that negative, so this piece is positive. I should be looking here. This piece is positive. I can take the square root of it, add it to that, and divide by a positive number. So VO2 comes out to be positive. So it passes a couple of quick little checks. Other than that, I just have to trust my algebra.